Hello, fifth grade. All right, we are y'all are my guinea pigs, so you have to bear with me. I'm learning how to do all of this screencasting and YouTube and everything. We're going to be starting today on page 237 in your science books. You can either follow along with your science book or you can just watch this video because I'm going to pull up every page for you so you can see. We're going to be starting our light chapter, which is chapter 10. We just finished our sound chapter right before everything went crazy. So chapter 10, light. All right, so I want you to imagine for a second that you are putting together a puzzle, and most of us, have probably done a puzzle at some point. And if you're able to see, it's a very easy thing to do, right? But if you can't see, it would be very difficult to put your puzzle together. So back a long time ago, it's probably hard to imagine, there used to not be ways for us to see inside of our body. And we're going to read here in a second about a lady called Marie Curie who created X-ray stations in World War I so that they could see inside soldiers' bodies to help take care of them. And this is just one of the many examples of uses of light and how we have, modern medicine and other things that we've discovered about light have been able to do really cool things like what we're going to read right here. So this chapter is going to be looking at things like that. It's going to be looking at just characteristics of light. It's going to be looking at the way, that talking about like how God designed light and in creation and those kind of things. So, all right, so we're starting on page 237. During World War I, there was an army dedicated to saving lives instead of taking them. This army of doctors and nurses cared for soldiers who had been wounded in battle. But how could they look inside a soldier to see what was wrong? Marie Curie, a Polish chemist and physicist, knew that the X-ray, a recent development in technology, would be helpful in solving this problem. She studied human anatomy and how to use the X-ray machines. She even researched how to work on cars. Then she gathered together 20 vans with the equipment for taking X-rays. She and her daughter drove to the front lines to help the doctors care for wounded soldiers. Her X-ray trucks were called Little Curies. By the end of the war, she had set up 200 X-ray stations in military hospitals. She also directed the training of many people in the use of X-rays. Because of Marie Curie's work, many soldiers healed faster and many lives were saved. So, something really cool. I'm sure many of you have had an X-ray at some point. I know I've had to take a couple of my kids for X-rays. I've had one myself, and because of light, that's something that we can do to see exactly what's going on inside of our bodies. It's pretty awesome. All right, so we're on 238 now. Let's look at light energy. The people who first discovered X-rays many years before World War I were surprised and amazed by what these mysterious rays could do. It was as if they were a kind of invisible light that could shine right through solid objects. X-rays share many of the same characteristics with light that you can see. Light is a form of wave energy. It is constantly moving throughout the universe. A light ray travels in a straight line, but the matter around it moves up and down. Light waves spread out as they move away from their source, like ripples of water move away from the place a pebble is dropped. So if you think about like when you've thrown like a pebble into a pond or a river or something, how that ripple effect coming out from it, that's how light does. However, light travels much faster than water. If you could travel at the speed of light, you would be able to go around the world about 7.5 times in just 1 second. Though light waves carry energy, just as other waves do, light waves are different from many other kinds of waves. The energy of water waves and sound waves must move through matter. Light waves, though, can move through both matter and empty space. Because light waves can travel through space, light and the sun and other stars can reach the earth. So, for example, if you were at the sun, no one would hear you on Earth, but the light gets to Earth. Light waves also move faster than other types of waves, such as sound. Light can travel through space at about 300,000 kilometers per second, 180,000 miles per second. The sun is about 150 million kilometers or 93 million miles away from the Earth, yet light from the sun reaches the Earth in about 8 minutes. Scientists do not know of anything that can travel faster than light does. So, this is a pretty cool fact here, this 8 minutes. So, like the sunlight that you're feeling right now left the sun 8 minutes ago. Pretty cool. All right. Science and history. One of the first scientists who tried to measure the speed of light was Galileo. In the 1600s, Galileo and his assistant stood on top of two hills that were about a mile apart. Each of them had a shattered lantern. Galileo flashed his lantern. As soon as the assistant saw Galileo's light, he flashed his own lantern. Galileo tried to time how long it took before he saw the answered flash of light. Since light travels so fast, Galileo was not able to measure the speed. More than 200 years later, another scientist, Albert Michelson, was able to make an accurate measurement of speed of light. He used a special 8-sided revolving mirror on top of a mountain in California. All right, so now we're going to look at the types of waves, comparing sound waves and light waves. Sometimes scientists classify waves by whether or not they can move through empty space. Waves that can move through space are called electromagnetic waves. Light is an electromagnetic wave. Waves that can move only through matter, such as sound waves, are called mechanical waves. Scientists also classify waves by the direction in which they move. Sound waves move in the same direction as the matter is vibrating. Waves that travel this way are called longitudinal waves, which is this right here. So we had that, slinky thing. We talked about compressions and stuff like that last time. So, here's our compression. But this is the direction the matter is moving, the direction of the wave. They go in the same direction. So longitudinal. Light waves move differently. If you make a wave with a rope, you can see the wave traveling from one end of the rope to the other. As the wave travels forward, the rope moves up and down. The direction that the wave travels is perpendicular to the up and down movement of the rope. This is an example of a transverse wave. Waves that move perpendicular to the way that the matter is moving are called transverse waves. Light waves are an example of transverse waves. So, as the rope is moving up and down, the direction is going this way, but the matter is moving up and down. So that is a transverse wave, which is light. All right, so let's look at properties of waves. There are many different kinds of waves. Some are tall, others are short. Some move quickly, but others move slowly. All waves, though, have the same basic properties or characteristics. These properties include wavelength, amplitude, frequency, and speed. Transverse waves look like a series of hills and valleys. The top part of the hill is called the crest and is the highest point of a wave. The trough is the lowest point or valley of a wave. Scientists use crests and troughs of a transverse wave to measure the length of that wave. Its wavelength is the distance between two crests or between two troughs. Waves with short wavelengths have more energy than waves with long wavelengths. So let's look at those parts now. So your valley is your trough, your mountain, your hill, or whatever you want to call it, is your crest. And then the difference between two crests, like this one, would be your wavelength, or the difference between two troughs would be a wavelength. Both of those are considered wavelengths, even though they're different from different points. They're still between the two. You guys are actually going to be drawing, one of your assignments this week is going to be drawing this picture and labeling it. So if you're wondering what I was talking about, it's this right here later on this week. So let's look at what this means as amplitude. So you see here in the picture that that's the distance from the rest position to the top of the crest, or from the rest position to the bottom of the trough. So let's read about that now. Another property of a wave is its amplitude. Amplitude is the height of a wave. If you stretch a rope tightly, it will be in a straight line. Think of this straight line as the rest position of a wave. Moving one end of the rope will make the rope vibrate up and down. Part of the rope will move above the rest position and make the crest of the waves. The rope will also move below the rest position, forming the troughs of the waves. The distance that the rope moves above or below the rest position is the amplitude or height of the wave. So imagine if this right here is your rope that is attached to the doorknob, like in the previous picture, okay, and you have it pulled tight, it's going to be this rest position. But when you start to move it up and down, okay, every time that it goes above or below, it creates what is called the amplitude, or that distance from the rest position to the height of or depth of your crest or your trough. All right, so then let's look at frequency now. So we've been talking about frequency with sounds, very similar with light as well. So our frequency and speed really are going to be the same definitions that we were dealing with sound. As the rope moves up and down, many waves move through it. Each wave has a crest and a trough. You can count the waves passing a point by counting either their crests or their troughs. The number of waves that pass a certain point in 1 second is the frequency of that wave. All right, so here's the start. 1 second ends here, and that's how many of these are in that spot. So these are the frequencies. 7 for this one, 9 for this one. You can see that these are closer together because they have a faster frequency. All right, so when we're talking about sound, we talked about how frequency is different from speed. So for example, you could be standing on a bridge and you could see cars passing under the bridge, like, picture like 81, okay? And so the cars are coming maybe at different speeds, okay? They're coming through, but their speed is their how far they go, their distance that they go in 1 second. So maybe the car is traveling at 60 miles per hour. That means in 1 hour, it's going to travel 60 miles, okay? So they could all be different. The frequency, though, doesn't matter how fast or slow the cars are passing under the bridge. The frequency is how many cars passed under the bridge during the time frame. So you could have, in just 5 minutes on 81, you could have, I don't know, 100-something cars pass. But that doesn't mean that they're all going 100 miles per hour. They're all going different speeds. A wave's frequency is not the same as its speed. Frequency refers to how many waves pass by a point in 1 second. Speed refers to the distance that one wave travels in 1 second. All waves have specific speeds, frequencies, amplitudes, and wavelengths. All right, so last little section here, science and math. The speed, wavelength, and frequency of a wave are related mathematically. If you know the wavelength and frequency of a wave, you can calculate its speed. Suppose a wave had a wavelength of 6 centimeters and a frequency of 5 waves per second. The speed of the wave would be 30 centimeters per second. Wavelength times frequency equals speed. All right, so that is our reading for today. If you guys have any questions on this, you can text, email. You can also post comments down in the comment section on the YouTube video, and I can respond back to those for you. So thank you for watching, and just let me know if you need help with anything. Bye, guys.